Okay, for today's breakdown, we are diving into a new paper from NVIDIA and the University of Rochester. PixelDiT, Pixel Diffusion Transformers for image generation.
And this one is, I think, really important because it's a fundamental challenge to the way we've been doing image generation for the last couple of years.
The latent diffusion model status quo.
Exactly. LDMs have been king, they're efficient, they scale, but they have what this paper argues is a fatal flaw. They all depend on a separately trained VAE, an autoencoder.
And that VAE, the variational autoencoder, creates this lossy bottleneck.
Yeah.
It's great for computation, squishing the image down, but it puts a hard cap on your final image quality. You just lose all that microscopic detail.
Precisely. So PixelDiT's whole mission is, simple. Get rid of the VAE. Just toss it out.
So it's a single-stage model, end-to-end, working directly in the pixel space.
No compression artifacts to apologize for. And the technical trick that makes it all work is this dual-level transformer architecture.
Right. So you have a patch-level DIT for the big picture, the global layout, and then a pixel-level DIT to handle all the fine-grained texture.
And they pull it off without the compute budget just exploding thanks to this really clever mechanism they call pixel token compaction. That's the key that makes pixel space modeling actually practical.
And the results really do speak for themselves. PixelDiT XL hits a new state-of-the-art 1.61 GFID on ImageNet at 256 by 256. That just blows past the other pixel models.
And it scales up to 1024 text to image, plus it shows way better content preservation and editing tasks. It's a huge argument for bringing focus back to pixel-level fidelity.
So let's start there. Let's revisit why we all accepted the LDM approach in the first place. It wasn't an aesthetic choice. It was a necessity.
Purely an engineering and a compute necessity.
Yeah. When DDPMs, the denoising diffusion probabilistic models, first came on the scene, running them directly on pixels was just brutal.
Oh, it was computationally savage. You're trying to run attention over millions of pixels. The complexity, it's quadratic, right? It's O of n squared with the number of pixels.
For anyone tracking the compute costs, that's just a non-starter. You double the image resolution, you quadruple the training cost. It was completely prohibitive for a long, long time.
So the VAE was the clever workaround.
Right. You just compress the image down to a much smaller latent space, maybe an eighth or a 16th of the size, and suddenly denoising becomes manageable.
And that's what unlocked high-resolution generation for, everyone who didn't have a dedicated supercomputer.
But it was a compromise. And that compromise has a real penalty.
It does. You're tying your main generative model to this autoencoder that was trained on a totally different objective, like a simple L1 or L2 reconstruction loss.
That's completely misaligned with the goal of generating a photorealistic image.
It is. It's like trying to build a skyscraper on a foundation that was designed for a shed. The VAE has already made decisions about what information is important.
It's the JPEG analogy, right? It's lossy reconstruction.
Perfect analogy. It aggressively throws out high-frequency details, subtle textures, sharp lines, because its only job is to create a decent-looking, coarse reconstruction. Once that detail is gone, it's gone forever.
So I could have the most powerful diffusion transformer in the world, but if it's operating in that latent space,
it can't invent details that the VAE already deleted. The ceiling on your final sample quality is set by the VAE, not your diffusion model.
And on top of that, you get these weird distribution shifts. The VAE might smooth out edges or change colors just a tiny bit.
And then your diffusion model has to waste some of its capacity just learning to compensate for the VAE's mistakes. It's inefficient.
So PixelDiT had to solve this two-part problem, model fine details, but do it without the insane computational cost.
And that's where their architecture is so smart. It's all about an intelligent division of labor.
Let's get into that dual-level approach. It's one single end-to-end pipeline, but it has two distinct jobs. So how does that first level, the patch-level DIT, work?
The patch-level DIT is all about the big picture. It's built for speed and global structure, so it uses really aggressive patchification, like a patch size of 16 by 16.
Which keeps the token sequence nice and short.
Exactly. So it can afford to do that long-range attention, figuring out the global semantics, the overall layout, the what and the where.
And for text-to-image, this is where you inject the conditioning.
Right. They extend it with what they call multimodal DIT blocks, which is how they fuse in the text embeddings from a frozen encoder like Gemma 2.
So the output from this first stage is basically a set of instructions. It's the semantic context, let's call it scond, that tells the second stage, okay, here's the layout, now go fill in the details.
That's a great way to put it. And that's when the second stage takes over, the pixel-level PIT blocks. This is the part of the model that's obsessed with fidelity.
Its whole job is just local refinement, getting the textures just right.
Dense per pixel modeling. But this is where you'd expect the computational costs to explode again.
Yeah, if you're suddenly operating at the pixel level, how do you avoid that O of n squared nightmare we just talked about?
They have two very clever tricks. First, that pixel pathway uses a much, much smaller hidden dimension dpix. So maybe it's only 16, while the main patch pathway is using a much larger dimension. That helps a lot with memory.
Okay, but the real secret sauce is in the modulation and the compaction. Let's start with the pixel-wise AdaLN modulation. Standard AdaLN is efficient, but it's kind of blunt.
It is. In a normal DIT, you'd have patch-wise modulation. You take your semantic token, you compute some scale and shift parameters, and you just broadcast those exact same parameters to all 256 pixels inside a 16 by 16 patch.
So every pixel in that block gets the exact same update instruction.
Which naturally causes smoothing. You lose local variation.
So what PixelDiT does differently is it gives every single pixel its own unique set of instructions.
Precisely. They use a tiny MLP that takes the semantic token, the scond, and expands it. Instead of one set of parameters for the whole patch, it spits out p-squared sets of unique scale, shift, and gating parameters.
So for a 16 by 16 patch, that's 256 unique instruction sets.
Exactly. Every single pixel gets an independent context-aware update. And that's how you preserve those really fine-grained textures that patch-wise modulation just flattens out.
That fine-grained control is huge, but you still have the attention problem. If you try to run global attention over all those pixel tokens, the whole thing would just fall over.
It would. You'd run out of memory instantly. And that brings us to the second big innovation, pixel token compaction, or PTC.
This is the crucial part. How do we know this isn't just another VAE, another lossy bottleneck with a different name?
That's the million-dollar question. And the difference is in the intent and the implementation. The VAE permanently compresses information for representation. PTC is a temporary trick used only for computation.
Okay, so walk us through how it works.
So right before the global attention operation, it takes all the p-squared pixel tokens inside a patch.
All 256 of them.
And it uses a learned linear map to compress them down into a single compact patch token. This is where the sequence length just plummets.
You go from a sequence of H times W pixels down to just L patch tokens.
For a 1024 by 1024 image, that's taking a sequence of over 1 million tokens down to just 48096. It's a 256x reduction. The drop in attention cost is just enormous.
And the key is that the fine-grained information isn't lost.
Right, because it's preserved through residual connections that bypass this little compaction step. So when the compact token is expanded back out after attention, the high-resolution texture information is still there, waiting to be used. The ablations prove it too. If you turn off PTC, the model immediately throws an out-of-memory error. It's absolutely essential.
So that's the distinction. It's temporary compression for a calculation, not permanent compression for representation.
You've got it. That's the whole game. All the efficiency benefits, none of the fidelity drawbacks of a VAE.
All right, let's talk results, because this is where the paper really makes its case. On ImageNet 256 by 256, the PixelDiT XL model gets a 1.61 GFID. For anyone who follows these numbers, that is a massive leap for a pixel space model.
It is a huge leap. It's not a small incremental bump. The previous state-of-the-art pixel models, like PixelFlow XL, were stuck around 1.98. That gap between 1.98 and 1.61 visually is very noticeable. We're talking sharper images, more believable textures.
And the really compelling part is that they've almost closed the efficiency gap. We accepted latent models because they were so much cheaper to run, but PixelDiT XL gets this result using only 311 GFLOPs.
Which is so competitive. A highly optimized latent model like DiT XL2 is about 238 GFLOPs. The enormous gap that justified the existence of LDMs is, well, it's pretty much gone.
So you're getting pure pixel fidelity for only a very small compute trade-off now.
And it trains fast. It hits a GFID of 2.36 after only 80 epochs.
Which is crazy when you compare it to older pixel models like ADMU, which needed 400 epochs just to get to a 4.59 GFID.
The efficient architecture just makes the whole learning process so much faster.
And because it scales so well, they were able to go straight to 24 by 24 for text-to-image generation, which was basically impossible for older pixel models.
And the results there are right up there with the giants. The scores they report put them in the same league as models like FLUX Dev and DELI 3. They're competing at the highest level without a VAE.
For me, though, the most convincing evidence is the image editing example, using FlowEdit. This is where you can physically see the VAE's weakness.
Oh yeah, this is the killer visual. You take an image, and you do a simple local edit, say, changing a bicycle in the foreground into a motorcycle.
And the big latent models like Stable Diffusion 3 or FLUX, they do the main edit, but then they mess up the background.
Because the VAE's lossy compression has already damaged the original image. When the model tries to decode the latent space back into pixels after the edit, it can't perfectly reconstruct the parts of the image that weren't even touched.
Exactly. They show this example where there's some text on a brick wall in the background, far away from the edit, and the latent models just turn it into garbage. The VAE threw away the high-frequency information needed to render that text cleanly.
But PixelDiT, because it's working in pixel space the whole time, it doesn't have that problem.
It changes the bicycle to a motorcycle and leaves the background text perfectly intact.
That kind of content preservation is a massive win for any practical workflow that involves editing or manipulation. It shows these VAE artifacts aren't just some theoretical problem, they have real practical consequences.
Let's touch on the ablations quickly, because they show how carefully this thing was engineered, the layer allocation, for instance.
Right. They experimented with how many layers to give to the patch part versus the pixel part. They found the sweet spot for the XL model was 26 patch layers and 4 pixel layers.
And interestingly, adding more pixel layers didn't really help. It actually slowed down convergence.
Yeah, which suggests that you only need a moderately powerful, dedicated pathway to refine the texture. Anything more than that just makes the optimization harder.
And the patch size trade-off for the biggest model was also really telling.
For PixelDiT XL, the performance difference between a patch size of 8 and a patch size of 16 basically disappeared.
Which makes 16 the obvious choice because it's so much cheaper computationally. The model is powerful enough that it doesn't need smaller patches to see the details. It has the pixel pathway for that.
And maybe the most counterintuitive result was with the pixel token compaction rate.
Right, they tested different levels of compression.
And the most aggressive compression, the 1x rate, actually performed slightly better than the less compressed versions. It was also the most efficient, of course.
Which suggests the essential information for texture is actually very, very compact.
Yeah.
And trying to work with longer, more redundant sequences might just be harder for the model to optimize.
It's just really solid, meticulous engineering.
So to wrap it all up, the big achievement here is that PixelDiT basically proved that the problem with pixel space diffusion wasn't the pixel space itself.
No, it was just that we didn't have the right architectures to model it efficiently.
They've closed the efficiency gap, they've closed the fidelity gap, and they've done it without the huge downside of VAEs. It feels like pixel space models are officially back in the race.
In a very big way.
Which brings us to a really fascinating question for you to think about. PixelDiT hits these incredible numbers with only 1.3 billion parameters. The paper itself notes that it still has some limitations with really complex geometry like human hands or intricate architecture things that are typically solved with just more model capacity and more data.
So the question is, how much further can these end-to-end pixel space models go? Now that the architectural bottleneck is gone, what are the remaining limits beyond just scaling up the model size and improving the data quality? That's what we'll be watching for next.